and there we have done the reactivity of group 16 elements with hydrogen. We have done with oxygen, and today we'll do with halogen. Okay, so reactivity with halogen. So we'll write now here group 16 elements react with halogens to form halides of the type EX2. Please remember here oxidation state of P16 is 2 plus 2. EX4, where oxidation state of the group 16 element is plus 4. And EX6. So E is equal to what? E is equal to sulfur, selenium, tellurium, polonium. All right. So now, other than that, see, this is called dihalide, tetrahalide, hexahalide. But other than that, they also form monohalides. Okay, so I'll start with this. Anyway, this is not in your book. We'll write now, yeah. Other than that, they also form monohalides. Okay, so let us see. See, halogen means what? Earlier we have talked about hydrogen and oxygen. So only one element was there. Now when you say halogen, there are 4 halogen atoms are there. They are fluorine, chlorine, bromine, iodine. So you should know which is more stable. This stability of monohalides. It is fluorine is more stable than chlorine, than bromine, and iodine does not. Okay. So now we can see one of the example. We'll write now here OO2F. It is very interesting. It is this only in this compound oxygen shows oxidation state of +1. We'll write now here. Oxygen, this is for entrance exam, and this is in your book also. Oxygen forms only O2F, known as oxygen fluoride. It is the only compound where oxygen shows an oxidation state of plus 1. Okay, it is not that stable. I told you that many thing which is not in your book, I'm writing it is only to help you in your entries. Okay. Now, these monohalides undergo disproportionation. Okay, I'll write down here. Sulfur shows dimeric monohalides. Okay, so these also exist in dimer. See why? The valency of oxygen is not 1. Valency of oxygen is 2. Okay, I'll write down its structure here. So if it is like this, then valency of oxygen is not satisfied. So this is the way. So what is this? 1:1. Because of that, we call it, we write the formula, we call it oxygen monochloride, but formula is O2F. Okay. So if you wish, here you can write in bracket, please. Sulfur forms dimeric monohalides. Okay. These are S2, F2, S2, Cl2, S2, Br. Acha. And it also forms S2I. S2I. These monohalides undergo disproportionation. I have already told you disproportion in group 15. Okay, see here. 2Ac2 Cl2. The oxidation of selenium is +1. So it undergoes disproportionation to form AcCl4 and 3Fe. See, here it is +4 and here it is 0. I told you, if any of the oxidation state of a compound is not stable, then they undergo mutual loss and gain of electrons to form two compounds where oxidation state of one is higher than the previous and second one is lower than the previous. See here, 4 is more than this, 0 is less than. This is there in your book. I don't know whether present book is there or not. Now we'll go for dihalides. Dihalides will be what? EX. All the elements except selenium or dihalide. Okay, example I can write here now. OF2 is called oxygen difluoride. Okay, then you can have here now S2F2, S2, sorry, SF2, SCl2, SBr2, etc. All this. Okay, then selenium does not form. Tellurium dichloride, tellurium dibromides are. Now we'll go for tetrahelix. All these elements form tetrafluorides. Please remember, whenever you go to the higher oxidation state, more electronegative element will form, more electronegative halogen will form. So in that case, you'll find fluorine will form, bromine and iodine will not form. Okay? Tetrafluorides, as this simple thing you will remember on the basis of electronegativity, then life become very easy. Because higher the oxidation state means you have to pull out the electron. See here, you should understand here. So it is science. See now, this is the electronic configuration of group 60. Now, if you want to have tetra halides, you must have 4 unpaired electrons. 4 unpaired electron is possible only when you break this pair. So, who is going to break the pair? It is any element who has a strong tendency to pull others electron. Who can do? This is with high electronic. So, this electron will be pulled here. All right. So, who can do? Most electronegative element is fluorine, followed by chlorine. Other than that, they cannot. Because of that, you write all these elements from tetrafluoride as well as tetrachlorides. Bromine and iodine will not. Okay, it is only you know, right? I don't want my student should buy hard chemistry. Okay, they have sp3b. This is important for your. This is there in your book. I think this is important for your hybridization. And have C so geometry. Remember your class 11 geometry. Okay, well, how does it look like? See here. In this case, this is the lone pair. Say it is, I have taken here now sulfur tetrafluoride. This is important. It is given in your book on also. This is actual geometry, but it should have been trigonal bipyramidal, but electron you cannot see. Only these are visible. So this is C. So C. So anyone you have taken sulfur, selenium, tellurium. If the moment you go for the tetrahalides, you'll have this geometry. Okay, if it is tetrachloride also, geometry is same. All
Done,
right.
sir.
Now, hexahalides. This is there in your book. Hexahalides. Among hexahalides, only the hexafluorides. This is the highest oxidation state, and that can be achieved only by fluorine. Fluorine also is there; it can also form, but it's not that stable. Only hexafluorides are stable. Okay, hexafluorides means what? EF6. Excuse me. Hello. তোমার কথাটা স্পষ্ট না, আবার বলো। হ্যাঁ হ্যাঁ বলো। হ্যাঁ না লাগবে না, মগ্নমেরু জিনিসগুলো ভালো না, সাবস্ট্যান্ডার্ড ঠিক চলে আসে। মা তো আজকে নিয়ে এসছে, মা ওই মগ্নময় বিল্ডিং এর কাছে তুমি জিজ্ঞেস করলে হবে ইলাহুই, এটা বিরাট উঁচু বিল্ডিং আছে ওখানে, মা কিনেছে তো আজকে। হ্যাঁ মা তো অলরেডি, ইওর মাদার অলরেডি পারচেজ। কি বলো? আচ্ছা দিচ্ছি। হ্যাঁ পাইছে পাইছে। আচ্ছা, only hexafluorides are stable. It has sp3d2 hybridization and octahedral okay, then how does it look like? It is E can be sulfur, selenium, anything. Its hybridization is sp3 and structure is octahedral. So this is the structure. See here, F. Please don't think that is in the plane of the board. No, not there like this. Okay. See. So it is like this. This is the plane. See, this is the plane, and this is the structure. One fluorine is here, another is here, another is here, another. Clear? So this one. Now see, very interesting. See, you have remembered the dipole moment in class 11. See, any element and fluorine bond is extremely polar because fluorine is strongest electronegatively. So this molecule should have very high dipole moment. But dear, see, this bond moment is cancelled by this. This is being cancelled by this. This is being cancelled by this. So this type of molecules are non-polar. So right now, these molecules are non-polar. Non-polar means what? They have very less intermolecular forces of attraction, and because of that, they exist in gaseous state. These molecules are non-polar. Covalent. Okay, I'll not write because some of them may be liquid also. Because if you go down the group, these molecules are non-polar and covalent in nature. Okay, so let me take one example of SF6. So I'll write now here sulfur SF6. So we'll write now here. SF6 is covalent, non-polar, and gaseous in nature. Okay. Now try to understand. This is chemically inert. This line is not mentioned in your book. This is chemically inert. And even does not undergo most thermodynamically favorable reaction like hydrolysis. Now why? Very good question. I know, because you will never ask me. This is the advantage of teaching to students of Shillong. They never ask question. Outside, if you go, you cannot complete your sentence also. You can't tell people question will immediately come. Why? So again, I'll draw it. Okay, I'll draw it like. See here. Look, such a small sulfur atom is being surrounded from all sides by fluorine. So it doesn't allow water molecule to reach up to sulfur. Huh? Well, what will write down? This is because small sulfur atom is sterically means space. Huh? Sterically what should I write now here? Is being surrounded by 6 fluorine atoms, which creates steric hindrance, means obstruction of space due to space. Steric hindrance, which creates steric hindrance and does not allow water molecules to attack sulfur atoms. Now, little bit for your entrance exam, because this you may remember, it does not react, but in entrance exam they will not give this. They will give you this selenium hexafluoride. Then you will also say it does not react. No. See here, selenium is a large atom. Look. See, if you sit across a small dining table, hardly any space is there to serve you. But your dining table is large. and number of people are same. See, so much gap is there. So in that case, selenium hexafluoride, tellurium hexafluoride, tellurium hexachloride, they react with water. Okay, because they do not have a problem of space. So if you have added water here, it will give you I'll write now here 6 8 F, and it will give you 6 8. It will give you AC with 6. So because of the larger 6. Okay, so now, so with this, the group discussion will finish. We'll go to now individual molecules. So first one is oxygen. Oxygen, I don't feel like teaching because you have already studied still. Okay, I'll do it. Right now here, O2, we call it dioxide. Because whenever you say oxygen means element. Element symbol is O. This contains 2 oxygen atoms. Because of that, we call it dioxygen. So you know, oxygen is found in free state in our atmosphere, and it is the most abundant element on Earth. See, most abundant element in the universe is hydrogen, and most abundant element in the Earth is oxygen. We get in free state in air, we get in combined state because 2/3 of the Earth is covered with water, along with so many minerals containing oxygen. Okay, so its preparation. By different techniques, we can prepare oxygen. Okay, I'll go for now. First one is that laboratory preparation. In laboratory preparation is what? Any compound which contains proportionately more amount of oxygen, they decomposes to give oxygen. So what we can write down? Any compound which contains proportionately more oxygen decomposes to liberate oxygen. So what I can write? First one which you have done in school is potassium chlorate, KClO3. Potassium chlorate. I'm not going to write the name. This one you have done in school. See here, 1:1:3. So if you heat it in presence of catalyst like manganese dioxide is catalyst, if you heat it, you get what? 2KCl plus 3O2. Okay. Now I'll write here potassium nitrate or sodium nitrate. See here 1:1:3. So if you heat it, here you don't require catalyst. You will get now here potassium nitrite plus oxygen. If you have heated potassium permanganate, see 1:1:4, you will get down here K2MnO4. Okay, I'll write down the name here. Potassium permanganate. This is violet in color, deep violet. This is called potassium manganate. Okay, this is green in color. Plus you will get manganese dioxide and you will get oxygen. Okay. So these are having proportionately high. So let me write it here. 1. Second, B. Some metal oxides that I have already told you in some basic this thing isolation of elements. Some metal oxides on heating produce oxygen. Okay, these are two examples are there. This is mercuric oxide. Okay, the mercuric oxide and silver oxide. See here, this is silver oxide. I told you that if you go to jewelry shop, they put it into fire, then the portion which has become black because silver oxide is black in color. So if you heat it, what happens? The oxygen goes out. See here, you are getting pure silver. He doesn't do anything but charges so much money because he knows chemistry and you do not. Okay, so this same is the case with mercuric oxide. Mercuric oxide, if you heat it, you will get now mercury and you get now peroxides. Peroxides on heating. I have written a plenty. This is for your entrance there. So much thing is not there in the book. Peroxides on heating also liberate oxygen. All right. So I have taken here barium peroxide. This is called barium peroxide. So if you heat it, it will give you barium oxide. Your knowledge of chemistry is so meager, so because of that it creates a problem for me. Okay. Hydrogen peroxide. So if you heat it, you get water and oxygen. This one you know, I need not write. Okay. PbO2, lead called lead dioxide or lead peroxide. Same equation. If you heat it, you get PbO plus O2. Okay. So now, how to prepare commercially? Oxygen you require huge amount, mind it. Huge amount of oxygen is required in industry. So, second one is commercial preparation. So here A, oxygen is commercially obtained by fractional distillation of liquid air. I told you nitrogen. You liquefy air. From this liquid, if you go for fractional distillation, first nitrogen will come, followed by oxygen. So by liquid, yeah. And second, we obtain by electrolysis of water in presence of catalytic amount of acid or alkali using platinum electrodes. See here now. First I write the equation, then I'll show you how it is. So here I'll write H2O and it gives you hydrogen and oxygen. I'll balance it. Okay. Here I'll write H plus catalyst. So small amount of acid is being added. And here I'll write electrolysis. So cathode and anode. So you know water gives you what? See, water breaks down to give you H plus and OH minus. So here I'll write 4OH and here I'll write 4H plus 4 electron give you here G and here. So it is not costly. See, this time due to COVID, second wave of COVID, so many people died because of lack of oxygen or because of our carelessness and attitude of the present government. But generation of oxygen is not that costly. Oxygen, pure oxygen is already being made in steel plants and various metallurgical industries. Government did not bother. If the common people die, nothing happens to the presidential government. They are not bothered. They are only bothered for the rich people. Okay, but COVID has made you something to realize. Whether rich or poor, in front of disease, all are same. So this is the preparation of oxygen. So about the properties of oxygen, what should I say? Physical properties. I'm not going to write. You know it. Oxygen is a colorless, odorless, tasteless liquid, and it is sparingly soluble in water. That is, a small amount of oxygen is soluble in water. Very small amount. All right. So before I go to the chemical properties, I like to tell you, just as I told you that the nitrogen behave abnormally from other elements, oxygen also behaves abnormally from the other elements. So here we write chemical properties. So here we write abnormal behavior of oxygen. So we write oxygen does not behave like other elements of the group. Means what? Sulfur, selenium, tellurium, and polonium. Okay, that is, does not behave like sulfur, selenium, tellurium, and why? This is because of its one small size. Second, high ionization enthalpy. Third, more negative electron gain enthalpy. Four, ability to form p pi p pi. When I say p pi p pi, don't get scared. It is a pi bond. But why do you call it p pi p pi? Because the p orbital of oxygen combined with p orbitals of another element. Because of that, it is called p pi p pi. Ability to form p pi bond. And fifth is very important one. See, other elements, sulfur, selenium, tellurium, polonium, they show oxidation state of +4, +6. Oxygen can never extend its valency beyond 2. I already told you in the group discussion. Why? Because it does not have a d orbital. So what should I write now? Here, absence of d orbitals.
আলু আনিসনি গুড্ডু নো পটেটো পটেটো
Acha, one more thing I have to supposed to write. Okay, I'll write in other. Now reactions. Oxygen generally does not react at ordinary temperature. Ordinary temperature means room temperature. Ordinary, all these words you should know because of that habit. Ordinary temperature. Why? Because of its high bond dissociation and see, remember, if I go sulfur, the bond is single. If I go for oxygen, this is the bond, double bond. So you require more energy. So what should I write now here? Because of its high bond dissociation enthalpy due to oxygen double bond. So it reacts at higher. I can give you an example, very simple example. See, if you keep the coal outside, it is exposed to air. Air has 20% oxygen, but coal does not burn. But moment you heat the coal, means you have supplied heat to the coal, that time it combines with oxygen. And you will find entire amount of the coal will burn. What does it mean? That oxygen will combine with coal or any other substances only when you supply heat. Right? Because in that case, you break this double bond and it becomes oxygen atom and oxygen atom. Okay. So now I'll write here. Okay. Reaction with non-metals. First we'll write here carbon, oxygen, it gives you carbon dioxide. Okay, this I write here now excess. Then I can write here carbon. It is, see here, this is 1:1, and this is 2:1. That is, I can say it is less. So what will write now here? Insufficient. What will give you? Carbon monoxide. Due to that, you will find, suppose in winter season, people in Shillong or in the villages, especially Shillong, it does not happen these days. Villages people use coal, burn coal to warm their room. But as because doors and windows, everything is closed, it produces a lot of carbon. Initially, it forms carbon dioxide. Later on, oxygen becomes less. It forms carbon monoxide, and carbon monoxide is highly toxic. Because of that, you will find many people are dying. Okay. Then sulfur will give you sulfur dioxide. Nitrogen and oxygen does not react. Why? Nitrogen has triple bond, oxygen has double bond. You have to break all these bonds, so it requires very high temperature. So how much temperature you require? 3273 Kelvin, or what? Thunder. Then only it forms nitric oxide. But phosphorus burns. Phosphorus, you find that moment you take white phosphorus, huh? moment it comes in contact with oxygen, it reacts. Why? Not because of oxygen, because I told you that white phosphorus is not stable because of angular strain. So what it will give you? It will give you P4O10. Okay, metals now. Metal. Most of the metals. What will write now here? Most of the metal except the noble metals like what? Gold and platinum. Palladium also. Not platinum, rhodium. Gold, platinum, and rhodium reacts with oxygen. Then what should I write? Okay. So I'll write now here. Lithium. Oxygen. It will give you lithium oxide. Sorry. Very sorry. Lithium is valence is 1, oxygen is 2. So if you have taken sodium, immediately reacts. Why? Because they have very less ionization enthalpy, these alkali metals. So you'll get now here sodium oxide. If you have taken magnesium burns with a white flame in oxygen. So it will give you magnesium oxide. Right? Then comes aluminium. Okay? So it will give you, sorry, it will give you Al2O3, it will be 4. So it will be 2, 6, yes. So aluminium, Al2O3. So here I will write. Note. Al2O3 form sticks to the surface of the metal and does not allow further reaction because it's surface. It coats the surface so the aluminum from inside they do not react. So what do you call this one? We call it passive. So it becomes passive. Now if we have taken here iron, it's okay. The iron reacts with oxygen in presence of what? Moisture to form what? 2Fe2O3. Okay. So this is what? This is rust. So this most of the thing which I have done, it is done in present at room temperature or little heating. Okay. So now I'm going to write something which is important.
Done, sir.
Okay. So I'm going to write something which is not given in your book, but is important. This is reaction of alkali metals with oxygen on heating. Reaction of alkali metals. What are alkali metals? Lithium, sodium, potassium, rubidium, and cesium with oxygen at higher temperature. They react at room temperature, but if you heat, you see very interesting. So right now 4 lithium O2, it will give you 2 Li2O. Lithium oxide. Heat. Now, if I have taken sodium, earlier I have shown same reaction, but if you take sodium, it is not like this. If you have taken here sodium, sorry, it will give you Na2O2. It is called sodium peroxide. Now you have taken potassium. If you heat it, you get now here KO2. This is called superoxide. If you have taken rubidium O2, if you heat it, you get here now superoxide. If you have taken cesium O2 on heat, you will get here this. So these are called superoxide. Potassium superoxide, rubidium superoxide, and cesium superoxide. Okay, now reaction with compound means oxidation. Reaction with compounds. Or oxidation. So suppose you have taken here zinc sulfide, you know this is called what? Roasting. So what you will get now here? You get now zinc oxide plus sulfur. If you have taken ammonia, that you have already seen or solved process, what do I do? Told you 45, 46. This you put down bridges of platinum at 1100 Kelvin. What you get now here? You get nitric oxide and water. Okay. This will be doing later on. Sulfur dioxide, oxygen. Okay. It is 725 Kelvin, and if you do in presence of vanadium pentoxide as catalyst, you get here sulfur dioxide. Okay. If you have taken HCl and O2, if you have taken here cuprous chloride as cupric chloride as catalyst and 773 Kelvin, it will give you 2H2O plus 2 chlorine. All these things you will get it. All this. Okay. Now if you have taken CH4, you know this is CNG. We are using it as a fuel. So what it will give you? It will give you 2H2O plus carbon dioxide. So these are the things. So now we'll go to ozone.
Done, sir.
Okay. So now we'll go to ozone. Ozone is an allotrope of oxygen. Ozone. It is an allotrope of oxygen. It is generally found in the upper atmosphere. You know it very well. Ozone protects us from ultraviolet light. Okay. Sometimes ozone is also found over the ground. Maybe sometime in mines, or sometime you find our vast agricultural field before rain occurs. It sometimes it generates. Okay. So how to prepare? It is prepared from oxygen by passing silent electric discharge. Don't worry. I'll tell you how it's done. In ozonizer, this is the instrument where we prepare. Okay. Very bad drawing. Okay. See here. Dry oxygen. Dry and pure oxygen is being sent. This is blocked. Inside this tube, you have a electrode, metal plate, and outside you have a metal plate. That is, if this is a metal plate, then this is the metal plate. Oxygen flows through this. Oxygen never comes in contact with the metal of the electrodes. Okay, and high voltage of electricity is passed through that, and in that way, what will happen? O3. All right. So what here I'm going to write the equation here. 3O2, please see it is a reversible reaction, gives you 2O3. And this is a very strange thing is that this is an endothermic reaction. Let me say its value. I think it's minus 86 plus 86. No, it is delta H is plus 142.7 kilojoule. So I'll write down here. 3O2. I have so many things to tell on it. So it is 2O3 delta H is plus 142.7 kilojoule moles. Okay, kilojoule mole inverse. See, look, moment you see it is plus, then you know this reaction is not spontaneous. That is, oxygen doesn't want to form ozone. Because of that, see, little disturbance, the ozone is being breaking down to oxygen. Okay, so what do we write now? This reaction is reversible and non-spontaneous. So what will happen now? There's every possibility is that this will like to come to the left hand side. We'll write now. The equilibrium of the reaction has a tendency to shift towards left. Means what? Its decomposition will be very fast. Then what should I write here? This arrow I'll make it small. Means small amount of there, large amount is again comes back. Why? Why it is so small? Because of two thermodynamic reasons. I'll write here. Because towards left, because of thermodynamic factor. See why? A reaction which is non-spontaneous from left to right is spontaneous from right to left. Huh? So in that case, what are the conditions of spontaneity? See here, we know that delta H should delta G should be delta H minus T into delta S. If delta G value is negative, then it is spontaneous. But we have already found is positive. So reverse will be what? The reverse will be always negative. See why? Because delta H is endothermic. If I write this equation ulta, what is going to happen here? See here. 2O3 gives us 3O2. So in this case, delta H is negative. Okay, so it is 285 point this kilojoule. You don't have to remember. I have to write to make you understand. See here, in reverse, it is exothermic, means negative. So this ozone will immediately decompose to give you this. What is the second factor? See here, is the entropy. 3 molecules gives us 3 moles of oxygen gives us 2 mole of oxygen, ozone. But when it breaks, 2 mole of ozone gives us 3 moles. As the number of the oxygen molecule increases, entropy increases. As the entropy increases, the reaction always moves to the other side. All right. So what do you find? That when you go for making ozone, a large portion of the ozone gets converted into again oxygen. Now, if you have prepared a large amount of ozone in one place, this may cause explosion. Why? Because as it breaks down to give you oxygen, in that case, what you find? It will produce so much amount of heat, it will blast. So what will you write now here? Accumulation of large amount of ozone in a place can cause serious explosion. Why? Because it will generate huge amount of oxygen and heat, which causes the explosion. So if you want to carry out any reaction with ozone, we always take oxygen containing less amount of ozone. This is called ozonized oxygen. 10 to 50% amount of the ozone is there. Still over. Okay, so now we'll go for its property. Physical properties. It is a it is a pale blue gas having pungent odor. Okay. chemical properties. Ozone is a strong oxidizing agent as it produces nascent oxygen. See now, nascent oxygen means atomic oxygen. What does it give? O2 and so this is the one which oxidizes ozone. Okay, right? Then I will do it. Okay. So now we'll do. Only 2 reactions are there in your book, so I'm going to take 2 only. Then we'll write here 1. Oxidation of lead sulfide. This is black. Ozone oxidizes black lead sulfide to colorless lead sulfide. Why I'm writing the color? Because this question they will ask you like this. What happens to the black lead sulfide when it comes in contact to ozone? You have to write that it forms colorless lead sulfide. Okay, so again here I'm going to do in partial equation. So O3 will be O2 plus O. See here PBS. What is the product? PBSO4. See, life becomes so simple. How many oxygens are there? 4. I'll write it down here. 4 oxygen. Who will supply this oxygen? First step. So you have multiplied by 4. Feel me. You don't have to buy hard. PBS 4 into 4O3 PBSO4 plus 4. Do like this. One put মাসের মধ্যে একটা গন্ধ হচ্ছে। Second, oxidation of potassium iodide. Ozone liberates iodine. Potassium iodide solution is colorless. And if you pass ozone, you'll find the solution has become violet. Ozone liberates iodine from potassium iodide. So I'll write now here. O3 gives you O2 plus O. Okay. Now, then after that, I'll write here 2 potassium iodide H2O plus O. It will give you potassium hydroxide and I. Add. So 2 potassium iodide H2O O3. It will give you potassium hydroxide I2 plus O.
Done, sir.
See, this equation is extremely helpful to find out that how much ozone is there in the mixture of ozone and oxygen. Okay. In laboratory, suppose you want to carry out a reaction, but before reaction, so you must know that how much ozone is there in that mixture. So what you do, first we do this reaction. We do this reaction. Okay. And after that, to that reaction, we add right now. This reaction is used to estimate the amount of ozone in ozonized oxygen. A standard solution of sodium thiosulfate, we call it hypol, is used to titrate the amount of liberated iron. I'll do it and I'll explain to you. Because I find that you never ask me any question. And this habit you will not leave also. All right. So I cannot force you to ask me question. Na? So Na2 S2O3. This is okay. I'll write down the formula. Na2 S2. See here, what is liberated iodine? So you will get now here 2 sodium iodide and Na2S4O6. This is called sodium tetra ionic. See here, because you know how much sodium thiosulfate you added. You know by weight. See, very interesting. In this reaction, this is 1:1. In this reaction, it is 2:1. And this is 1:1. So if you can find out how much amount of iodine is liberated, where from you get it? From this value. So whatever the value you get, half of it is iodine, and exactly that much amount of ozone is there in the mixture. So this reaction is useful. Okay. So finished. Okay. Now see here. So with this we finish the oxygen and ozone. One thing which I did not teach you, but it is there in my copy, is the oxides. This is a part of your class 11. Because of that, I did not teach you. Now, I'll give you a little bit of homework. Is sulfur. You don't have to do anything. Sulfur, you please read the allotrope. Okay, sulfur has many allotropes, but out of that, in your book, what is given here? You'll find here rhombic sulfur, monoclinic sulfur, plastic sulfur. This thing you please read from the book, and the copy in which you are writing my class note, please write there. Then it will be content. This I'm not going to discuss with you. Thing which I'm going to just spend around 5-10 minutes. See, sulfur exists in S2, S4, S6, and S8. Okay, now S2. S2 exists in gaseous. It is paramagnetic due to the presence of two unpaired electrons in anti-bonding pi see here anti-bonding. Okay, I'll write remove pi anti-bonding pi star on. This is very, very important for exam. So now in class 11, in the chemical bonding chapter, do you remember you have drawn the molecular orbital diagram of oxygen? Huh? Molecular orbital diagram of oxygen. Have you drawn for oxygen? Molecular orbital diagram. So this is also one more thing that you have to check in your copy today in your class 11 book. Book 1 of class 11. There you see the molecular orbital diagram of oxygen. So in oxygen, you have 1s2, 2s2, 2p, but in sulfur, you'll find in oxygen, in antimony oxygen, see, it was like this. Okay, I'll do. This I'm doing for oxygen. Everything you forgot. See here. So it is 1s, 2s, 1s, 2s, 1, 2. So it is this is sigma to pz. This is pi to px to a pi to py. Yes. Then it is pi star y, pi star to p x. Here 1, 2, 3, 4. See, these are these two unpaired electron remains in the pi star orbital. But when you go for sulfur, then it will be here, it will be 3px, 3py, 3pz. Forget about this bottom one. 3py, 3px, 3py, 3pz, like this. So in that case, what is going to happen? This is for oxygen. So let me rub the bottom portion. So I will convert this one into 3px, 3py, 3pz, 3, 3, 3. So it will be 3, 3, 3, 3, 3, and this is sigma star GP. See, you have to unpair electron. So existing case, it is paramagnetic due to the presence of two unpaired electrons in antibonding pi orbital. So this one you draw. And after that, I'll draw more structure. Then good night for today. So I'll put few structures for you. So this allotrope today I'll read it. And the place where you are after finishing this one, there you'll write small paragraph from the book. You need not write the entire thing. Whatever you feel important, you write. See now, how does S4 looks like? The structure of S4 is this. From this one, rhombus. Then how does S6 looks like? See, this is called chair form. Right? This is S8. Okay, S8. So what we will call this structure? Have you seen any structure like this?
No, sir.
Yes, you have seen. Have you not seen any beauty contest? Huh? The champion is given something like that, na?
Yes, sir.
You call it
Crown.
crown. So this structure is called crown. Okay, so you'll find in rhombic sulfur, the structure is that this type of thing remain the same form. And in monoclinic structure, if one is like this, the next one will be just mirror image of this one. So this is called crown. S8 is crown structure. So with this I finished, and tomorrow we'll meet. So tomorrow I'll try to finish sulfur.